Hey everyone! Today we're going to understand one of the most revolutionary technologies in artificial intelligence, transformers. Now, I'm not talking about robots that turn into cars. I'm talking about the AI architecture that powers ChatGPT, Google Translate, and pretty much every major language AI you've heard of. By the end of this video, you'll understand how transformers work using simple, everyday examples. No PhD required, I promise. Smash that subscribe button, Part 1. The problem before transformers. Let's start with a simple question. How do you teach a computer to understand language? Imagine you're reading a sentence. The cat sat on the mat because it was comfortable. Easy for you, right? You instantly know that it refers to the mat, not the cat. But for a computer, this is incredibly difficult because they were doing the old way called RNNs, recurrent neural networks. Before transformers, we used something called RNNs. Think of RNNs like reading a book one word at a time, but you can only remember what you just read a few pages ago. Here's the problem. Imagine reading, "The chef who won multiple awards in France, Italy, and Spain over the last decade finally opened a restaurant in New York." By the time you get to opened a restaurant, you've almost forgotten about the chef at the beginning. That's the RNN problem. They struggle with long-range dependencies. RNNs also had to process words sequentially, one after another. You couldn't skip ahead or look at multiple words simultaneously. This made training incredibly slow. Part 2. The Transformer Revolution. In 2017, researchers at Google published a paper called "Attention is All You Need." And they literally meant it. The transformer architecture solved both major problems. 1. It could look at all words in a sentence simultaneously. 2. It could understand relationships between any words no matter how far apart. Think of it like this. Instead of reading a book page by page, you can now see the entire book laid out in front of you at once, and you can instantly draw connections between any two sentences, even if they're chapters apart. Part 3. The core concept, attention mechanism. Now let's get to the heart of transformers, the attention mechanism. Simple example, the dinner party. Imagine you're at a dinner party with 10 people. Everyone is talking, but you need to pay attention to different people based on what's being discussed. When someone mentions football, you pay more attention to your friend who's a sports fan. When someone says cooking, you pay more attention to the chef in the group. You're still aware everyone else is talking, but you weight their words differently. That's exactly what attention does. Real language example. For example, in this sentence, the animal didn't cross the street because it was too tired. Now let's see how a transformer, like the one behind ChatGPT, figures out what it refers to. When the transformer processes the word it, here's what happens. Step 1, the transformer. Gets curious, query. When the model reaches the word it pauses and basically asks, who or what is it talking about? This internal question is what we call a query, the model's way of searching for meaning in earlier words. Step 2, searching for clues, keys. To answer that question, the transformer looks back at all the previous words in the sentence. The, animal, didn't, cross, the, street, because. Each of these words acts like a key, a piece of stored information that the model can compare against the query. Step 3, measuring relevance, attention scores. Now the transformer tries to figure out which word is most related to it. It gives each earlier word a score. Higher means more relevant. Animal, high score, 90%. Street, low score, 5%. The, very low score, 1%. Other words, low or near 0. This process is called attention. The model literally pays more attention to words that matter. Step 4, combining the clues, values. Finally, the transformer blends information from all those words, but gives more weight to the ones with higher scores, like animal. It takes bits of meaning, adjusts them by their scores, and produces one combined understanding. Finally, the transformer understands it, and the animal. I am simplifying the math for you. You don't need to understand all the math, but here's the intuition. Q, the query means, what am I looking for? K, the key means, what do I have? V, the value means, what information can I provide? Think of it like a library. Query, I need books about cooking, what you're searching for. Keys, labels on bookshelves, what each section is about. Values, the actual books, the information you get. The attention mechanism matches your query with relevant keys, then retrieves the corresponding values. Part 4. Multi-head attention. Here's where it gets even cooler. Transformers don't just use one attention mechanism, they use multiple ones in parallel. This is called multi-head attention. The group study example. Imagine you're studying a complex topic with friends. Instead of everyone focusing on the same thing, you divide up. Person 1 focuses on understanding who is involved. Person 2 focuses on understanding when things happen. Person 3 focuses on understanding why things happen. Person 4 focuses on understanding where things occur. Then you combine all your insights. In Transformers, each attention head learns to focus on different aspects. Sentence: the chef made delicious pasta yesterday. Head 1 might focus on subject-verb relationships. Chef, made. Head 2 might focus on adjectives. Delicious, pasta. Head 3 might focus on temporal context. Made, yesterday. Head 4 might focus on object relationships. Made, pasta. By combining multiple attention heads, the transformer builds a rich, multidimensional understanding of the sentence. Part 5. Positional encoding. Remember I said transformers look at all words simultaneously? Well, there's a problem with that. The word order problem consider these two sentences. 1. The dog bit the man. 2. The man bit the dog. Same words, very different meanings. Order matters. But if the transformer sees all words at once, how does it know which came first? The solution. Positional encoding. Imagine giving each word a unique ID badge that tells its position. Word 1 gets badge. 1.0, 0.0, 0.0. Word 2 gets badge. 0.5, 0.87, 0.0. Word 3 gets badge. 0.5, 0.87, 0.0. These are special mathematical patterns, sine and cosine waves, that encode position information. The transformer adds these position codes to each word, so it always knows where words appear in the sentence. Think of it like GPS coordinates. They tell you exactly where something is located. Part 6. The full transformer architecture. Now let's put it all together. A transformer has two main parts. The encoder, understanding input. Think of this as the reading comprehension part. Layer by layer. 1. Input embedding. Convert words to numbers, vectors. Hello becomes 0.2, 0.8, 0.3, 0.1. 2. Positional encoding. Add position information. 3. Multi-head attention. Understand relationships between words. 4. Feed-forward network. Process and refine understanding. 5. Repeat 6 to 12 times. Stack multiple layers for deeper understanding. Example: the cat chased the mouse. After encoding, the transformer has a deep understanding of who did what, the relationship between cat and mouse, the action, chasing, the sequence of events. The decoder, generating output. This is the writing part. It generates new text. How it works. Let's say we're translating the cat chased the mouse to Spanish. Step 1. Start token. Ready, set, go. Before generating any words, the model begins with a special start signal, kind of like saying, "Okay, I'm about to start translating now." This tells the model it's time to begin producing the output sentence. Step 2. Masked self-attention. Remember, don't peek ahead. When generating each new Spanish word, the model can only look back at the words it's already produced. Never forward. That's why it's called masked attention. The mask hides future words so the model doesn't cheat. Example: when predicting gato, it can't see persiguió yet, only the start signal. Can only look backward, not forward, can't cheat. Step 3. Cross attention. Check the original meaning. Now the decoder looks at what the encoder understood from the English sentence. It's basically asking, what did the English phrase mean again? This step connects the source, English, and the target, Spanish, ensuring the translation stays true to the original meaning. What did the English sentence mean? Step 4. Feed-forward network. Choose the next word. Finally, using all that context, the model runs the information through a feed-forward network to predict the next word, for example, deciding that L should come first. Output: El gato persiguió al ratón. The decoder generates one word at a time. First, L, then using L, generates gato, then using el gato, generates persiguió, and so on. Part 7. Real-world examples. Let's see transformers in action with real scenarios. Example 1. Language translation. English: I love to eat pizza. Spanish: Me encanta comer pizza. The encoder understands I, subject, love, emotion, action, to eat, activity, pizza, object, sentiment, positive, context, food preference. The decoder generates Spanish, converts I love, me encanta, more natural in Spanish, keeps pizza, pizza, international word, restructures grammar to match Spanish patterns. Example 2, text completion. Input: The weather today is sunny, so I should probably. The transformer. 1. Understands context, sunny weather. 2. Recognizes common patterns, sunny, outdoor activities. 3. Generates logical completions. Wear sunscreen. Go to the beach. Have a picnic. Example 3. Question answering. Context: The Eiffel Tower was completed in 1889. It stands 324 meters tall and is located in Paris, France. Question: How tall is the Eiffel Tower? Attention mechanism in action. Query: How tall focuses on measurement words. High attention on 324 meters tall. Low attention on 1889, Paris. Answer: 324 meters. Part 8. Why transformers are so powerful. Advantage. 1. Parallel processing. Old RNNs process words one by one, which is slow. Transformers process entire sentence at once, which is fast. This means training is 10 to 100x faster, can handle much longer sequences, more efficient use of computing power. Second advantage, long-range dependencies. Remember our example. The chef who won multiple awards opened a restaurant. Transformers connect chef and opened directly, even with 10+ words in between. Advantage 3. Transfer learning. Here's the game changer, pre-training. Step 1. Train on massive amounts of text, like reading millions of books. The transformer learns language patterns, facts, reasoning. Step 2. Fine-tune for specific tasks, like learning a specialized skill. Translation, summarization, question answering. This is why ChatGPT can do so many things. It learned from huge amounts of internet text. Advantage 4. Scalability. Transformers scale beautifully. More data, better performance, bigger models, more capable, more training, more knowledge. GPT-3 has 175 billion parameters, like having 175 billion knobs to tune. This massive scale enables emergent abilities we didn't even train for. Part 9. Limitations and challenges. Transformers aren't perfect. Let's be honest about the challenges. Challenge 1. Computational cost. Transformers are powerful, but that power comes at a price. Every time a transformer processes a sentence, it tries to understand how every word relates to every other word. That's the magic of self-attention, but it also means a lot of calculations. Let's see how big this gets. If your text has 1,000 words, the model has to compare each word to all 999 others. That's 1,000 multiplied by 1,000, which equals 1 million word pairs to analyze. Now compare that to an older model like an RNN, recurrent neural network, which just looks at words one after another. So it only does around 1,000 operations. That's 1,000 times increase in computation in case of transformers. This is why training large transformers requires massive computing power, memory, and energy. Think rows of GPUs running for weeks or even months. Challenge 2. Context length. Most transformers have a maximum context length, example 2048 or 4096 tokens. Imagine reading a book, but you can only remember the last 20 pages. For really long documents, transformers still struggle. Challenge 3. Reasoning limitations. Transformers are pattern matchers, not reasoners. They might generate plausible sounding but incorrect information, struggle with complex math or logic and might miss subtle context or sarcasm. Fourth challenge, data requirements. Training large transformers requires millions or billions of examples, weeks or months of computing time, and millions of dollars in resources. Part 10, the future. So where are transformers heading? Here are 4 trends. Trend 1, efficiency improvements. Researchers are developing sparse attention, don't look at every word. Linear attention, faster computation. Smaller models that perform just as well. Trend 2, multimodal transformers. Not just text anymore, vision, audio, and combined models. Vision transformers for images, audio transformers for speech. Combined models, text plus image plus audio. Example, DALL-E and Stable Diffusion use transformer-like architectures to generate images from text. Trend 3, longer context. New models are pushing boundaries. GPT-4 can handle 32,000 plus tokens. Research models are reaching 100,000 plus tokens. The goal is to process entire books at once. Trend 4, specialized applications. Transformers are being adapted for drug discovery, predicting protein structures. Adapted for code generation, GitHub Copilot. Adapted for scientific research, analyzing papers. Adapted for creative arts, music, art, writing. Let's recap the key ideas. 1. Attention mechanism. Transformers can focus on relevant information by calculating attention scores between all words. 2. Parallel processing. Unlike older models, transformers process entire sequences simultaneously. 3. Multi-head attention. Multiple attention mechanisms work together to understand different aspects of language. 4. Encoder-decoder architecture. One part understands input, another generates output. 5. Scalability. Transformers get better with more data and computing power. The transformer revolution happened because of one simple but powerful idea. Let the model decide what's important by paying attention to it. From translating languages to writing code, from answering questions to generating art, transformers have transformed AI, pun intended. And we're just getting started. The next few years will bring even more incredible applications we can't even imagine yet. Thanks for watching. I hope this helped demystify transformers. Remember, at their core, they're just really good at paying attention to what matters. If you found this helpful, please like and subscribe. Drop a comment below if you have questions or want to see more AI deep dives. And remember, attention is all you need. See you in the next video.